free to read the book on those sections. So I'm going to start with the 1.5, which is the design engineers ethics. Okay, by the way, as I said, I'm going to post all these things. So you feel free to not take notes, just follow. If you want to take notes, that's fine too. Okay, so clearly one of the responsibilities is to satisfy the needs of the client. Of the client. You need to communicate all things required in writing or through presentations. Okay, so then there are other responsibilities in terms of design. Your design should, a designer should understand the problem, should formulate the formulation, state all assumptions, which is really something which is of utmost importance. All assumptions. So then analyze, evaluate, and present. Okay, now another way which you can be, one of your things which people do is they become active members of their society. And so some of you might be members of ASME, active members of your society. So by being an active member, you typically as a junior member, you probably learn from your seniors, but as you become a senior member, you sort of train other members, right? So that's a great way to give back to your society. So the society which many students at UIC join are the American Society of Mechanical Engineers. So it doesn't end here. You can actually be a professional and also be a part of ASME. So I'm, for example, a part of ASME. And one of the things I do as a member of ASME is I review journal papers, I submit journal papers, I take part in conferences. Sometimes you also get a chance to mentor and give talks to clubs. But there are other people who are working in industry who are part of ASME, and they actually actively contribute to ASME. I'll talk a little bit more about ethics in a presentation just a bit. There is this really good set of videos by this professor from Purdue. I think he's retired now, Michael Louis, and I'll actually try to put some in your homework. You just have to watch some videos and answer questions. So Michael C. Louis on ethics. Okay, and then I'm just going to give you a presentation. And I think the presentation, we will end the class. Presentation on ethics. Okay, so professional ethics is one of the key things which we don't quite emphasize so much in our studies, but it's very important. So, the discipline of dealing with good and bad, okay, with moral duty and obligation. So it's important to understand what the right and wrong behavior is,
And I'll give you an example of that in a bit. So each association has its own code of ethics. So ASME has its own code of ethics. In fact, you can go online and search for code of ethics, for example, ASME code of ethics, and it'll give you all your responsibility as a professional engineer. So what is paramount is that you abide by these code of ethics. So here's an example of something pulled from the ASC code of ethics, as the American Society of Civil Engineers. So it says that, and I quote, engineers shall hold paramount the safety, health, and welfare of the public, and shall strive to comply with the principles of sustainable development in the performance of the professional duties. So here is an example where this could be applied. So imagine you're a civil engineer working for a company that specializes in road construction. Okay, and so you're working on the roads. But when you working on the road, you notice that a bridge section is actually there is some problem in a bridge section, which is not your job. So in such a situation, should you ignore what you observed because you're working on the road and not on the bridge, or should you report that? Okay, so when we are, many times when we see something which is not our responsibility, we say that, or we're not trying to do, we say that we shouldn't report it, or we shouldn't say anything about it because it's not our job. But it turns out that the code of ethics tells you that you are responsible for that. So the right thing to do, if you see something which is professionally is not right, then you should report it. You should go and tell that what you saw, perhaps to your supervisor, and then he or she takes it from there. Okay, so it's important to follow those codes of ethics. That's why it's important to read the code of ethics for a field. Here's another example. So on January 28, 1986, 7 astronauts were killed 1 minute into a flight of the Challenger. And what happened was that the engineers found that there was a faulty design, and then the engineers brought this issue during testing to the higher authorities, which were probably not engineers; they were probably administrators. And but the administrators actually ignored the warnings of the engineers, and that was, there were a few reasons in that scenario. There was political pressure. The political pressure was because I think it was maybe it was Reagan who was trying to seek a second term, and so there was this pressure to get the mission going. There was economic pressure because I think there was a similar program in Europe, and they were trying to they were also sending, they were also sending people in space, and so they wanted to uh, so they also wanted to do this as fast as possible. There was competition, and then what had happened is that this mission was delayed several times. So there was so much pressure on the upper management, and they did not follow the advice of the engineers, and eventually this catastrophe happened. And this was a very well documented example of where the ethics were not followed. Okay, so subsequently now you don't see so many of these disasters because of ethics, because when such things happen, you probably have mechanisms in place to ensure that they don't happen again.
Okay, so standard is it's essentially a specification for either materials, parts, or processes. And the reason why we want to standardize things is because we want to reduce the variability. And once we reduce the variability, things become easy to mass produce. So set of specification for parts, materials, and also processes. Okay, the reason why we do that is to reduce variability. And turns out that standards are set by the company which is going to either design them or set them. So set by designer or the manufacturer. Now, codes are slightly different from standards. They are also a set of specifications um, for the analysis, design, and construction of an object, but they are actually set by the state or federal government. So once they're set by the state and federal government, they are bound by the law. And if you don't meet those codes, then you are in trouble because then somebody can sue you. So set of specifications for the analysis, design, manufacture, and construction of an object or objects. The goal here, like variability, is here to actually set the safety and efficiency and performance requirement, right? And this is something which the government cares about, needs to be safe and efficient and safe to use. So these are set by either the local government or the state government, local or state or federal government. And since they're set by the government, they carry the force of law. Okay, so the book gives a list of standards and codes. For example, the Bearing Manufacturers Association has its own standard, the gear manufacturers have their own standard, and so on. So here's something you can do if you want to search for a standard. Then you could, for example, search for, and this is on Google, search for ISO ASTM standard. If you want to look for a possible code, here is one from ASME, boiler and pressure vessel. And these codes are, if you go and search, and I did that some time back, these are like pages and pages of documents. So unless you're in this industry and you're really manufacturing or designing something, then you really won't be looking for these things. But once you start doing it, you are supposed to know where to find these things. And I believe that these standards are not, so the codes are not free. You need to pay to get them. But if you're in a company, then you probably have access to them because the company has already paid for it. Okay, so let's move on to economics now. Okay. Anything in the industry is driven by either ability to sustain or to produce a profit, right? So cost plays a very important role in all kinds of design, right? Cost plays, because you need to have people whom you need to pay, or sometimes you also need a cost to buy equipment or upgrade equipment, and cost varies with the location, material, and labor. Okay, so something which is easy and cheap to produce in, say, a developing country is probably much more expensive in developed countries. So that's why you see many of the things are outsourced to other countries, because maybe labor is cheap, or maybe even the material is cheap. So when we think about economics and to keep things inexpensive, you want to always think of ways to standardize parts, processes, and so on. So what we do is we use um, sizes from a catalog. And the reason why you do that is because the sizes from a catalog are pretty much mass produced. So for example, if you want a shaft, you might want to buy a 50 shaft or 60 shaft, but something which is like 53 or 57 is probably not in the catalog. And if you want that, you'll probably incur more cost because then it has to be custom made to suit you. So then other thing is you need to ensure that items are in stock. So sizes are available and in stock. So for example, if you have an item, a size say 50 which is more popular and found in the catalog of many vendors, then you probably want to stick to 50 and not standardize to 60 So those are important things. And then the other thing which people check is discounts for bulk orders. Okay, so that's one thing. The other thing which is important for economy is tolerances. Yeah. So what I mean by tolerance is if you make a shaft of 50 and if you make hundreds of pieces, then you'll see that all shafts won't be exactly 50 they will be plus or minus 50 okay. So when we make and that's because the world is not perfect and you can't just assume that when you manufacture it with a even with an expensive machine you get exactly what you want. So there is uh, tolerances is dimensional variation. An example would be, as I said, is you want a shaft, it could be 50 plus or minus 5 okay? Or it could be maybe 50 plus or minus 10 which means that if you randomly choose a shaft in this lot, then it would be either somewhere between 40 and 60 okay? What you can see here is that this has a larger tolerance than the first one. In other words, the first shaft is much more precise than the second one. It turns out that more precise you may want to make an object, the more expensive it gets. So here is a diagram which I shared on the handout, right? So this shows the cost on the y-axis and then shows the different machining operations to get, say, a particular diameter. So this is for steel. And so the way you read this is if you want, let's say, a shaft, and you want it to be accurate to plus or minus 0.03, then you probably only want to do a rough turn. So in this range, up to 0.005, a rough turn would do it. So this, when I say rough turn, it's probably on a lathe, right? If you want to make it even more finer, then you want to semi-finish turn it, which means that you do another operation after rough turning. So clearly more operations means more energy or more labor, which means it gets more expensive. And then if you want to do even more tolerant, if you want to make it even smaller tolerance, then you have to just keep adding more processes. And that what that does is basically it shoots up your costs. So you can see that the costs are uh, some number 100% of whatever, say, it's available in the market, but as you add these last two operations, it just shoots up all the way to 400%. So this is one of the things we want to care about when we want to manufacture something. It has to be economical. Okay. Now there is something called a break-even point, which every person has to worry about who gets into any money-making business, right? Money-making break-even point. So it's the point measured either in could be cost, could be time uh, at which two processes have the same return. So for example, if you are working on a lathe, and then you will see that there's certain costs to make parts. And now if you change that to a CNC, then you'll have a different cost. So if you want to figure out at what particular number of parts would you break even on CNC, then you will see that for CNC, perhaps you need to pay more money upfront. So there's more cost to buy it compared to a lathe. So clearly, after you reach a certain production level, maybe 5,000 or 20,000 units, you will achieve a point where CNC outperforms a lathe in terms of profits. And in which case, if your production is more than that number, break-even point, then you probably want to invest in a CNC and not into a lathe. And so here is a problem which probably illustrates how to compute the break-even point for a hypothetical problem. Okay, so again, this problem is in the handout. You have downloaded, you can continue with me, or if you want taken a printout, that's fine too.
Professor, can I ask you a question before we move on?
There are two machines, A and B, that may be used to produce a niche product. A has a setup time of 5 hours. It produced 20 parts per hour at the cost of $20 per hour. B, on the other hand, has no setup time. It produces 10 parts per hour at the cost of $60 per hour. Well, what is the cost at which one will break even on the quantities? The key thing here is that we want to find the cost at which we break even on the quantity, which means that at what quantity we'll see that A and B would have the same cost. Okay, that's what it asked. And then the question is, once you find the break-even point, if you are asked to produce 10 units or 10 parts versus 30 parts, which of these processes or machines will you use? Okay, so B depends on A, so let's go ahead and solve for A first. Okay, so let's write down a few things. Let's write things about A. For A, we have 5 hours setup. We have 20 parts per hour, and then we have $20 per hour. Now in this scenario, there is parts, there is hours, which is time, and then there is a cost. We only are concerned about two things here. We are interested in the cost and the quantity. So having anything in terms of anything else is difficult for us to interpret. So in this case, we see that we are also given the hours, right? And hours is really not in our break-even equation. So let's just try to eliminate hours altogether. We'll just put everything in terms of costs and quantity. So this is how you can do it. So the setup time is in hours, and we'll convert that to cost eventually. But first, let's focus on this part. So there's 20 parts per hour at $20 per hour. In other words, for A, it would cost $20 for 1 hour, and in 1 hour we can produce 20 parts, which means that $20 for 20 parts. Okay, effectively, by saying this, we've eliminated hours. Now, the other thing is the setup time. This is the time it takes for the machine to be set up, which is also in hours. We want to convert that to cost or hours. Now, cost or parts. Now, there is 5 hours of setup time. The question is, in 5 hours, how many parts can we produce? Well, we can produce 5 times 20, So in 5 hours, we can produce 5 times 20, which is 100 parts. Okay. Okay, I just saw the chat. Oh, my bad. I'm sorry about the chat. I'm beginning of questions. Let me do one thing. Let me try to answer the questions about this part first, and then I'll go back to the tolerance one. Okay. My bad on the hearing part. I think I had to my speakers were off. Okay, I should be able to hear you now.
Does this work?
I think I can hear you now.
I'll try it again. Can you hear me?
Yes, I can hear you now.
Okay.
You had a question?
Yeah, I had a question about like what you showed previously. I typed it in the chat, so like whenever you're done with this problem, we can get back to that.
Sure. Let me go ahead. I'm sorry about the speaker being muted and not seeing the chat. It's just that it's new semester. I'll just get used to it. Okay, let's just finish this and go back to the questions in the chat. Okay, so we have 100 parts in 5 hours, and you could keep it in parts, or you could also keep it in cost. So if either you'll have 100 parts, which means that you'll incur $20 for 20 parts, so you'll incur $1.20, sorry, 200. My bad, $100. This pen, here it is. So to produce 100 parts, you would need $100. So that's the cost of producing 100 parts. So when this machine is sitting there idle for 5 hours, you've pretty much lost $100 because you would have been able to produce 100 parts, and that was not possible. So let's represent Y as the cost and X as the number of parts, just to make equations. So the cost of producing items on machine A consists of 2 parts. One part is the setup. That setup is the cost is 100, and then once you have done with the setup, then you can start producing parts. So that's going to be $20 for 20 parts. So $20 for 20 parts, and this will be multiplied with the number of parts. So if you take this quantity, which is dollars per parts, and multiply by the parts, you will end up with dollars, right? And that's why I have 20 divided by 20 times X. So I can actually write this as 100 plus X. Yeah, so that's the equation for the cost of using machine A. Now let's do the same for B. For B, we have 10 parts per hour at the cost of $60 per hour. So 10 parts per hour at $60 per hour, and which means that again we have hours here which we don't care about, so we just have to convert that to cost and parts. So we'll incur $60 for 10 parts, right? Because if you pay $60, we'll have 1 hour worth of work, and in 1 hour you can produce 10 parts. This is a question. So the question is, So the 100 is coming from us not producing for 5 hours, thus losing out 100. Yes, that's right. So the 100 in the first part is coming because we have lost that much of machine time because you need that time to set it up. For B, we can write the cost as there's no setup cost, so we put a 0 plus we have $60. So $60 for 10 parts times the number of parts, right? So times 6. So when you, so the reason I wrote this as the way it is because if you do parts, dollars per parts into parts, you'll have dollar amount. And so this will be 6x. Okay. Let me. So this part is setup. This is production. Similarly, we have the setup, which is 0, and then this is the production cost. Okay, let's call this equation 1. This one is equation 2. So let's write equation 1 and 2, and then if you want to find the break-even point, you basically have to equate the two because it's the break-even point is the point at which the costs in this case are equal. So we have y equals 100 plus x and y equals 6x. From these two, we can write 6x equals 100 plus x. And so we can write, well, you can solve for x in this case. So x comes out to be 20. And since x is parts, this is the number of parts or units. Okay, so this is saying that in order to break even, you need to manufacture 20 parts. And the best way this can be actually illustrated is through a graph. So in this case, since we are interested in costs and parts, what we do is we draw a graph of costs on the y-axis and the parts on the x-axis. And so let's make it 10, 20, 30, 40, and so on. And then the cost, since we're going to be, it's a good unit to use here. So we have 100 here. So we can maybe use, I think increments of 10 would be good. Or maybe 20 is good. 20, 40, 60, 80, sorry, 100, 120, and say 140. What I need to do now is draw the lines for the two machines. One of the machine is, this is A, and this is B. So for A, so if you remember, if you have equation y equals mx plus c, then the slope is given by m. Let me write that down. So if you have y equals c plus mx, then you know that this is the equation for line with slope m and intercept c on the y-axis. Where this intercept is going to be c. Right? Because if you put x equals 0, then y equals c, and then the slope is n. Okay, so given that information, it's kind of easy to now draw these curves. So first of all, y equals 100 plus x. The intercept is 100. That's the intercept. And then the slope is m equals 1. And so I need to draw a line which has a slope of 1. Something like this, 1, 1. And then for the other one, we have the constant is 0. So it has to pass through the origin. And then the slope is 6 times x. So it's going to be a steeper line. We just have to be mindful that it should intercept at x equals 20. So you could do this in your calculator, in which case you don't have to be so careful. just that I'm drawing it on paper, so I need to be careful about how I draw it. So let's just keep extending this like this. So this has slope of 6:1. This is machine B. This is machine A. Let's move it down. Okay, and then this is our break-even point. Turns out that the cost for the break-even point is exactly 120. So you can see it from this equation. So what you can do is to find the cost, all you need to do is put x equals all you need to do is put x equals to 20. So you'll have y equals x times 20, which is 120, or you can put x in this equation, which is x is 20, so you'll have 120. So that is the break-even cost. And then the quantity is this. So this is another way of doing the same problem without using equations. I mean, you of course need the equations unless that you cannot do the plot, but if you don't want to solve the equations, then this is what you do. Now the second part asks you to solve for, second part is which machine will you use for 10 units and which one for 30 units of production. And this is in terms of cost consideration. So you can actually do this much easily just by looking at the figure. If you look at this plot, okay, you can see that if you're on the left side of 20, okay, then the cheaper of the two would be going with machine B, because this line B is always below the blue line. The green line is below the blue line, or the line for B is below the A line. If you go anywhere to the right, then you'll see that the blue line is below the green line, which means that the cost for the machine A is less than cost of B. So it's obvious that for 10 units, what you would do is you would go for machine B, and for 30 units, you'll go for machine A. Now this, my drawing has a problem actually, I think. Yeah, it has a problem. It should be at 60, right? Because if you put x equals 10, if you put x equals 10, then you should get 60. So I should redraw it. Something like this. It's easier to draw with the graph paper. I should have chosen that option here. Okay, so when we have x equals 10, we have y equals 6 times 10, which is 60. And so you'll use machine B. And if you have x equals 30, which is right here, then you would use machine A. So the cost would be y equals 100 plus 30, which is 130. That would be machine A. So that this point, again, this figure is not quite right. Can modify this a little bit. Be 130, which is over here. Okay, my figure is badly scaled, but I hope you get the idea. So that's the answer. Okay, any questions on this? Okay, let me go back to the questions in the chat. Okay, I'm just reading out the question. why is it when tolerance gets smaller, the item becomes more expensive? So tolerance is like, if you go 0.00001, then you want to have a more processing of the material. So that is illustrated in this particular, right? You have more processes, right? You want to go from rough turn to grinding and honing to get a very fine tolerance. And as you have more processes, you have more cost. So the question.
The only thing that confuses me here is that when you get, like, for example, a rod that's 20 millimeters and then it has tolerance like plus minus like 5, let's say, that thing, right? That rod will be compatible with anything that's like 15 millimeters or 25 millimeters or 20 millimeters, correct?
Right.
So like what I'm confused about is like, why would people want, like, I get like precision might help with like how something will function, but like, why wouldn't people just want to have like more tolerance?
Sure. So I don't know if you have worked in some of these metrology labs where they have very high precise equipment because they are, for example, creating devices which will measure things. Like optical table is one of the examples where you see this. So there are applications where high accuracy is demanded and some applications where accuracy is not required. So for example, if you're driving, if you want to make a machine like a car, then you don't care too much about tolerance to an extent. But if you are now making a machine which will in turn make another machine which has to be super accurate because the vendor or because the application requires it, then you would need it. So it really is, it's dependent on the application.
Okay, I can see what you're saying. Like, when people make, I get it.
Okay, what are the other questions? Yeah, somebody has more precision. It's all the same thing, I think. Okay, I have a hard time scrolling this chat. Let me check something out. Yeah. Okay, so like all the questions are on that same point about precision. Okay, so looks like that's about it. That was the only question which people have tried answering in my absence. Thanks a lot. Okay, so let's see, what's the time? It's 1:35. Okay, let's move on. Okay, so this part is sort of, overview of what's going to come, which is a great deal of this course is going to be on understanding stresses, strains, and using stresses, strains to design elements. So we are at section 1.09 in the book. Okay, 1.09 stresses and stresses and strength should be singular, stress and strength. Okay, so I think we've used both these quantities before, but we've not really thought too much about what they mean in case of materials. They are actually have the same units, but they actually mean two different things. So stress is, as we know, is force per unit area, and so is strength. It's force per unit area. But we use stress to denote what that force per unit area is at a particular location on the object. So we say a normal stress of 5 megapascals, or which is basically Newton per meter square, or 6 kilonewton per meter square, and so on. But strength means that we are interested in the force per unit area of the object as a whole. So we say that steel has a strength of something. We don't say that's the strength at a particular point. So strength is associated with the with the material or the entire object, but stress is something which we measure or talk about in terms of what it is at a particular point. So both of them, stress and strength, are denoted as, are pretty much force per unit area. Okay. The way they differ is stress is at a particular location at a specific point on the body, while strength, which is the same units, is that which is to describe the at how do I put it? Strength is that, no. So it's the force per unit area for the object as a whole. Okay, and stress and strength is something which will come again and again, of course, and we'll be using this as we'll see. The stress has other things like normal stress, shear stress, what else? Radial stress, tangential stress, and so on. And these will become clear as we continue in this course. But there is a distinction, right, which is kind of important. Okay, and we'll come back to it in the next chapter. We'll leave it as it is. Okay, so the next thing is something which is kind of very important in design, which is known as the design factor and factor of safety. I think you might have heard of factor of safety, but not heard of design factor. So let me write down the definitions. So design factor. And we'll denote design factor with ND. And then there is something called factor of safety, which you might have heard of, which is denoted by N. Now, turns out that both of them have the same definition. Both have the same definition, just like stress and strain. So the definition is ND or N is nothing but the strength, okay, divided by the allowable stress. Okay, the strength will denote by S, and the stress, it could be normal stress or shear stress. Let's just put normal stress for now. Okay, again, as I said, strength is for the object as a whole, stress is the force per unit area at a particular point. So if they're the same definitions, how are they different? Well, it turns out that ND, which is the design factor, is computed before the design is complete. So it's computed before design is built. And N, which is the factor of safety, is computed after design is built. Okay. Now, you might think, why would there be a distinction? Why would the ND not be the same as N? And the reason why ND is not the same as N is because of standardization. So when you design something, let's say a shaft for a given radius, you will get some diameter, let's say 53. Okay, so if you get 53, and if you look at the catalog and you see that a shaft of 53 is not available, then you'll have to choose something which is available, which is probably something which is close to 53. So let's say that 55 diameter is available. So when you compute ND, your calculation will tell you 53, but when you actually use that in production, you'll use a 55 shaft. And that shaft will, when you use that shaft in the calculation, you'll find that the factor N will change. It will be the factor of safety, and that will be different from ND. And so the standardization is the reason why they are different. So standardization is the reason why N is not the same as ND. Okay, so I think this a problem will illustrate this best. So I'm going to solve a problem which will illustrate why N and ND are different. Again, this question was posted in the handout. Okay, a mechanical system requires a shaft. The shaft is subject to a normal force of 10 newtons and has a strength of 2000 Newton per meter squared and a design factor of 2. Find the shaft diameter and factor of safety. So the first thing to note here is that, let me just write this thing down. So we're given that the force is 10 newtons. The strength, which we'll denote by S, is 2000 Newton per meter square. And then we're given the design factor already. So the design factor is usually specified by the designer. What it really means is that when I read the equation, you'll see that it just shows you how beefed up your object is. So it can actually take stresses twice that what it is in this case, which will be clear when I write the equation, which is N equals strength divided by stress. So you see that if this is 2, that means that the actual item has a can bear twice the stress that normally can, which is a good thing because then it gives it more sturdiness, and if it is subject more load, then can take it. So we're given N, we're given the strength, which is 2000. We need to find sigma. So sigma is 1000. So sigma in this case is the stress, and that stress is again given the same units. Okay, now we are given the stress. Now we need to find the shaft diameter, okay, which will come from the equation for stress. The equation for stress is force per unit area. And we assume here in this case that this is some kind of a normal stress. If you have a shaft, it's subjected to a force, and this is the cross-section area. Then the stress is given by F divided by A. So stress is 1000, force is given as 10. The cross-section area in this case is pi d squared divided by 4. That's the area of a circle. And so we can solve for d. So d comes out to be, oh, a mistake here. Yeah, I should have written this as nd, my bad. This is nd. Everything looks okay. So solving for d gives 112.8 mm. So the answer to the question is, what's the shaft diameter? Well, it's 112.8. Now there's a problem though. If you try to procure something which is 112.8, then you'll see that the catalogs don't have this diameter. So what I did was, from the appendix, I pulled out a table. It's actually table A17, which gives me the standard dimension. So this is from the, if you go to the handout section, then you'll see that I've posted the appendix. This gives you a list of different standardized diameters for shafts. Okay, so we're not interested in inches, we're interested in millimeters. So that's what we want to look at. So starts with 0.05 millimeters, goes all the way to 300 millimeters. So we're looking for 112.8. And if you see 112.8, it's not available here. The closest diameters are 120 and 100. So you can choose one of those two. Okay. Now, turns out that if you actually use 100, you'll see that your factor of safety will go below 2. right? And you don't want your factor of safety to go below the design factor. You can try to do the calculation. So we always choose a diameter which is higher of the two. And the reason why that happens is because you'll see that the stress is inversely proportional to the diameter. So we have to choose, in this case, 120. Let's go back and choose. So from A17, we'll choose D equals 120, which is the larger of the diameter which we saw on the table. So that's the answer. Now let's go back and find the factor of safety, because now we've completed a design and we can build the shaft. So the factor of safety is now strength, same definition, strength divided by stress. The strength is a material property. It won't change. It will be 1000. The stress in this case is the force divided by area. So force is 10 divided by the area. So pi times diameter square. So 0.12 square divided by 4. Okay, so if you do this calculation, what comes out is n equals 2.26. Okay, so you see that the factor of safety is not the same as the design factor, which is 2. And the reason why it was not is because of standardization. We had to choose a diameter from the table. Okay? And what you can try to do is you can try to replace this with try replacing this with 100 mm, which we saw in the catalog, and you'll see that the factor of safety will come out to be less than 2. And you should never have a factor of safety less than the design factor, because that means that your design is it's going to be overstressed and it's going to fail.